Honors Algebra 2 Pre-Calculus. We're doing 1.4 in Algebra 2, which is direct variation and proportionality, or proportion, or any number of ways to say this. So, this is going to be a slightly vocab-heavy first video to talk about sort of different words and how they relate to the equations that we can get from them. So the first thing I want you to notice is that in all of the equations that I have listed over here on the right side of my board, you'll see a k, right? So just worth a note here that in all of these, k is called the constant of proportionality, or sometimes it'll be the constant of variation. It just depends on which book you use. So proportionality and variation are just sort of different words to describe the same thing. So what we're going to learn about today is we're essentially going to learn about 4 adjectives that can be used in front of the word variation that describe a specific mathematical situation. The other thing I want you to recognize is that you could replace the word variation with proportional or proportionality pretty easily. So direct variation is the same thing as being directly proportional. Okay, so that's my first note over here, is that k is the constant variation. My second note is that the phrase direct variation, right? The phrase direct variation is akin, meaning the same as, to saying directly proportional. Right, and the same thing would be true when we talk about inverse variation. That's the same as saying inversely proportional. So if you say something shows inverse variation or varies inversely, you could also say is inversely proportional. Okay, so you could interchange those two words. So if you've learned about proportionality but not variation and you're panicking, don't. It's the same concept, just a different way to do it. So just a different way to phrase it, rather. So the first thing I want to talk about is this vocabulary. So one of the things that gets limiting as mathematics gets more difficult is that mathematics can be a really exclusive club. The notations and the syntax and the vocabulary is really specific, and if you don't know what certain words mean or certain notations mean, you can feel like it's a foreign language, which it essentially is, and it's exclusive, and it makes you feel left out. It makes you feel sort of less than, no pun intended about math, with the idea of being less than. So it's really important, as much as you might think that vocab is something that is specifically in your English or Spanish or Chinese or French classes, it's really important to learn vocabulary in mathematics. And the same is true in science and in all of your classes. But I think in mathematics, sometimes we think about it as being all about the numbers and maybe sometimes about letters in the sense of variables, but not really vocabulary. And that's certainly false. The notation and vocabulary and syntax of mathematics is really, really important. Without those things, we can't communicate effectively. So when you see a phrase, you need to sometimes automatically equate that to an equation, and that's going to be the expectation when you take a college-level class, or when you take an AP test, or when you're sitting in whatever is your major in college, or if you're sitting in a higher-level high school course. The expectation is going to be that this phrase in your brain equates to this mathematical concept or this mathematical expression or equation, and that you need to know that. So let's walk through some vocab here. So I've listed the 4 different types of variation that your book addresses in this section. I've listed sort of the common phrases that you're going to see that go with it. And then I've given a sample of what the equation would look like that goes with that phrase, with the exception of the last one, combined variation, because that has just too many possibilities to have a typical common phrase. So let's start with direct variation. Remember that you could replace the phrase direct variation with directly proportional. It means the same thing. So one way we'll hear this is y varies directly as x. Okay, so y varies directly as x. The equation that this statement equates to is y equals kx, where k is some number. It's a constant in a particular problem. So in example 1, k might be 5. In example 2, k might be -3. In example 3, k might be -10/3. We don't know, but it's a constant. In each example or each practice problem, k is a numerical constant. So you see direct variation all the time in life. So essentially, direct variation is basically just a line with a y-intercept at the origin. So actually, when we talk about word problems, direct variation is basically anything that doesn't have an initial starting value or initial fee. So if, for instance, I told you that it cost me $10 to go to the movies, $10 per person, if I went by myself, well, that's $10. If I brought my son, well, assuming that they made me pay the same rate for a 2-year-old, or that I would bring a 2-year-old to the movies, which is a questionable choice, it would be another $10. So that's $20. And if my wife came with us, well, that would be another $10. So that's $30. And my cousin came with us, that's 40 because there's 4 of us and 4 times 10. So direct proportionality is something that you actually see a lot, right? So directly proportional or direct variation is something you see a lot. Essentially, it is a line with a y-intercept of 0. The second type of variation listed here is called joint variation. So joint variation is basically just direct variation with more than one variable involved. So y doesn't just vary directly as x, y is varying directly as both x and z, so instead of calling it direct, we say joint. But it means the same thing as direct variation. It's just saying that it is directly proportional to the product of these two quantities. So y varies jointly as x and z is simply y equals k times x times z. Okay? Inverse variation. Now, inverse variation is actually a really fun one to do word problems on, and we'll do some of those at some point soon. Inverse variation or inverse proportionality essentially means that the second variable, if y varies inversely as x, the x goes on the bottom. So instead of writing y equals k times x, we'd write y equals k over x. Again, k is still a constant. The other way you sometimes see this written is that if you were to multiply this x over, you would see it as xy equals k. So my favorite example of inverse variation in word problems usually involves, I'm going to call them person hours because calling them man hours really bothers me. So let's say that I want to paint classroom 209, and let's say I figure out that if I do it all by myself, it's going to take me 24 straight hours of work, like just 24 hours, putting the time in. Again, realistically, there's time for paint to dry and this, that, and the other, but let's say that I figure out that it is 24 hours of my personal labor to paint room 209. Cool. And I'm like, man, that seems really rough. But then maybe one of the other people on the staff volunteers to help me. Maybe Mr. Lead is like, cool, I've got you. And he comes in and he helps, right? Well, now, in theory, with Mr. Lead and I both working, it's still 24 person hours of work. But because there are 2 of us to split up those hours that are required, it should take us 12 hours because my 12 will be done simultaneously to his 12. So the product, so when I was the only person, me, right? So me, one person, did 24 hours and gave me a constant k of 24. But if it's now 2 of us, me and Mr. Lead as x, times the 12 hours we do, we still get the 24 person hours, right? If a third person volunteers to help, right? If Mr. Domers is like, no, I got you, I'll come in and help too. Well, now there's 3 of us doing that 24 hours of labor. So in theory, it's only going to take us 8 hours because those 24 person hours that are physically required to do the job will all be done simultaneously. So my 8 hours is at the same time as Mr. Domer's 8 hours is at the same time as Mr. Lead's 8 hours. Now, of course, in the real world, this is not a practical problem at some point, because at some point, too much help just doesn't help. Like, if I had 24 people total working, it's not going to take us an hour to paint the classroom, because if I have no room, if I'm standing like an inch from the person next to me trying to paint or trying to move something, it's actually going to slow me down, not speed me up. So sometimes when we do stuff like this in math, we don't actually take into account exact real-world conditions, and certainly there is that euphemism of too many cooks in the kitchen, right? So inverse proportionality or inverse variation totally works in lots of situations like that when you talk about something that takes a certain allotted number of person hours, but it doesn't really apply if you start to get way too many people doing the same thing. The last one here, which I don't give you an equation for, is called combined variation. So basically, combined variation is going to be a sentence that involves multiple of these statements. And then you would take multiple of these statements and you would write an equation based on the other rules we saw. The short version here is that both direct and joint variation mean the variables go on the top with the k. The only one where a variable goes on the bottom is if you see the word inversely. So this is going to depend on the sentence you're given, and we'll do practice like this in a couple minutes. It's going to depend on the situation you're given, but the key here is to think that inverse things land on the bottom of an equation. So the constant goes on the top, and both direct and joint would be variables on the top, but the inverse stuff goes on the bottom. So we're going to do examples of that in a couple minutes, but that's your little intro to this, to these types of variation, okay?